chapter 2 here, which is about measurements and all that good stuff here. So let's get going here. So remember last time we sort of finished up talking about scientific notation. And where's that slide? It's got to be here somewhere. There it is. And remember that a couple important things that we talked about with scientific notation. The first one, obviously, is it does need to be a number between 1 and 10. So remember that when we look at get something right with there, maybe come on. There you go. When we look at this part of it, this part before the times 10 part, if it writes, should again be a number between 1 and 10. Shouldn't be 10, 20, 30, 100. Shouldn't be a point number. It should be a number between 1 and 10. Times 10 to the n as well. And again, that exponent there should either be positive or negative, depending on which way you need to really move your decimal point to get a number between 1 and 10. More importantly, what we talked about is really what it says here, you know, how to use scientific notation with calculators. A reminder, again, you should have a exponent button, which as we have up here is an EE button. Again, an EXP button are the two common ones. And when you do really push those buttons, as I said last time, it does represent the times 10 part of the number, which essentially means that you shouldn't be hitting any multiplication button, no shift log buttons or anything crazy like that. And again, I think we went through and I kind of wrote out here really how to punch it into your calculator. You want to always make sure that you're using your exponent button as when you're doing something in scientific notation. A reminder as well, if you have sort of one of those newer sort of buttons, which again is one that maybe looks like this. As we talked about, nothing wrong with this type of button, but you do definitely have to put sort of parentheses around all the numbers in order to end up with the correct answer when it's all said and done. So you want to make sure you always punch them in correctly. Remember as well that, you know, your calculator will not necessarily give you the right or sort of give you the answer necessarily in scientific notation. Sometimes it may, and again, sometimes it may not. If we wanted to write this in scientific notation, again, looking at these two here, A, which is 64,000, it looks like, although there's not a decimal point here, we would need to go 1 place, 2 places, 3 places, 4 places to the left there, giving us 6.4 times 10 to the 4th. Remember, sort of a larger number will have a positive exponent when you do it. Here, we would actually need to go to the right 1 place and 2 places, gives us 2.1 times 10 to the minus 2. Again, sort of a smaller number should have a negative exponent. Any questions on those two there? We will talk here in the next chapter why, you know, we got rid of some of these zeros here and why maybe, you know, in some cases we may keep them. In other cases, we may kind of get rid of them. So that's basically what we just did there. So if we look at each of these here, looking for the correct scientific notation, again, we would need to go to the right here. 1, 2, 3, 4, 5, 6 places. And we would end up with 8 times 10 to the 6, which looks like this guy here should be our correct scientific notation. Coming this way, again, assuming that the decimal points here gives us 1, 2, 3, 4, 5, 6, 7 places. And that does give us a number 7.2, which is a number between 1 and 10. And again, it's a larger number. We went to the left there, which means we should end up with a positive exponent. Again, if we were going to punch that into our calculator, top one, for example, 8, we then hit the exponent button, and then we hit 6. And that's all you would hit there. And probably, again, it will look something like that. It may look something like this, you know, on your calculator. But, you know, this is the proper way to punch that into your calculator. Any questions on scientific notation there? Okay. All right, so that does wrap up pretty much chapter 1, as I mentioned. We're now going to move into chapter 2. Again, a reminder that the notes are up there on our Canvas site. And chapter 2, we're going to talk really about measurements. So it's all about how to properly take measurements, units, significant figures, all that kind of stuff. So let's get into sort of some really important parts about taking a measurement. First off, units and measurements. Units are extremely important. And whenever you take a measurement, you should always have units associated with it. So what I mean by that is, for example, if you just say, hey, congratulations, you have 100, there's really no frame of reference for what that 100 means. You could have like $100, which is probably pretty good. Maybe you have 100 straws, which I guess if you like straws is good. Maybe 100 apples. So there's really no frame of reference if you just say, hey, I have 100. So whenever we take a measurement, we always want to make sure we have a number, but we should definitely always make sure we have some type of unit there, which gives us sort of a frame of reference for what that number means. Clearly, if I have $100, I could probably go buy some straws if I want. But again, we have a really good idea of really what that number means. And when we sort of think about measurements or observations, there's kind of two types of observations. There's one that's referred to as qualitative. And a qualitative observation basically is just like sort of appearances. No measurements are made or anything like that. A solid formed, it turned purple, something like that. A measurement, on the other hand, is what is sometimes referred to as a quantitative. Basically observation. And that basically involves numbers and values that are going on. And, whenever we take any type of measurement, that's basically quantitative. So always really important, again, when we take a measurement, number and units there are really, really important. All right. So we see some different sort of measurements and values that are here on this page. We have 22 degrees Celsius. We have 12 kilograms, 58 kilograms. These are all values and units, which again, basically represents a proper measurement. Any questions on that there?
Yeah, Efron?
Yeah.
I have a question. It's on the slide before though. The zero. So I have a question on the 0.00008. You know how you went to the right side.
Yeah.
My thought process was, okay, if it's the right side, it's negative. My apologies. The next one before after
right here.
Yeah, there you go. Okay, so A1. When you had went to the right side, my thought process was I was assuming it was going to be a negative. But and then I understand if you go to the left, right, it's positive all the time, right?
Yeah, you're absolutely right. I'm sorry. I circled the wrong one. You are correct. I was incorrect here. I'm sorry about that. Actually, this is a small number, so I did definitely circle the wrong one there. It actually should be negative. So whenever it's a small number, it definitely should be -6 in this particular case. So you are correct. When you do go to the right, as I think we might talk about last time, you will get a negative exponent. And it should have been this one. Thank you for letting me know. I definitely circled the wrong one there. It definitely should be negative because it's a small number. That's a good way to remember it. This one here is obviously a very large number. And this should have a positive exponent as we do here. So yes, I might have said the wrong one as well. So I apologize on that, but it definitely should be this one here. Yeah.
Okay. So this for clarity. Okay. So the way I look at it is every time it's to the right, negative, to the left, positive.
Exactly. If you're going from the sort of decimal form, if you will, to scientific notation, that's correct. It's negative, and then positive if you go to the left there. Yeah, sorry about that. I definitely.
That's fine. Thank you.
No problem. Thank you for letting me know. Other questions on that or anything else there? Okay. Okay. All right. So let's talk a little bit about sort of units and so forth. There's really sort of two systems of units that are commonly used, and one is really the metric system, which is pretty much what everybody uses. And then there's kind of like the English system that the US uses a lot. And as you can imagine, if sort of the US is using the English system of units, pretty much everybody else there is using the metric system of units. As everybody's sort of doing business and working together, there could be some issues about that. And actually, in like 1960, they had a big conference on weights and measures. Sounds like a lot of fun. But they basically came up with sort of a standardized system of units. And you hear about a lot in chemistry, and sometimes what is referred to as the SI units, which, as you can see there, is the International System of Units. Truth be told, it really is sort of based off of the metric system. And sort of in chemistry, we use the SI units. And, for the most part, pretty much like the metric system is sort of what we use. We use it for things like length, volume, mass, temperature, and time. Here are some common sort of SI units that we come across here. This table is from your book as well. This is the metric system. The SI unit for volume is meters cubed. Meters for length is the unit of a measurement there. Mass is grams or kilograms. So I would say, we use kilograms a lot, meters a lot. Truthfully, we use liters a lot for volume, but the SI unit there is meters cubed. For temperature, this is one that maybe you may not be familiar with, but we do see degrees Celsius happen a lot. We definitely see this unit here pretty much in chemistry. If you have something to do with temperature or need a temperature value to put into sort of a formula or something like that, it usually needs to be in what is the units known as Kelvin. Kelvin is basically was used to be referred to as the absolute temperature scale. We talk about sort of degrees Fahrenheit, like when we sort of take our temperature, degrees Celsius. When we talk about Kelvin, and actually it's just Kelvin, that's one major sort of difference between the other two. We don't say degrees Kelvin or anything like that. We say something like 373 Kelvin. In terms of time, sort of the common unit there is seconds. And again, these are common sort of SI units that we use. And we really do sort of kind of like use the metric system here. And as we'll see, sort of prefixes and so forth, they sort of change some of these values. So let's talk about some of these quantities of measurement. First off, volume. Volume is really the space that's occupied by a particular substance. And there are several sort of units that we commonly come across when we're dealing with volumes. I would say for the most part, these three sort of units in terms of volume are what we come across. Liters is a very common unit of volume, again, abbreviated with an L. Also milliliters, which is basically sort of the prefix unit for liters as well. And cubic centimeters is another sort of volume here. That is cubic centimeters. There is a relationship that's also important to remember, that a milliliter is the same thing as 1 cubic centimeter. And then in medicine, sometimes people will use cc to stand for cubic centimeter. But this relationship as well, we kind of see and use a lot. So these are very common sort of units of volume. And you may be wondering to yourself, what about cubic centimeters? Isn't a centimeter sort of a length measurement? And a centimeter by itself is a length measurement. But if you take something like the volume, let's try it again. The length times the width times the height of, say, like a cube, for example, you take a ruler and you measure it in centimeters, and centimeters for this measurement and centimeters for this measurement. When you multiply centimeters times centimeters times centimeters, you do get cubic centimeters. and that is a volume. So each of these individual measurements are length measurements, but typically if you take sort of a length measurement and cube it, it becomes a volume. And that's why we see, for example, the SI unit here is meters cubed. Meters, again, is a length measurement. If you sort of take the length times the width times the height, that gives us the volume that's represented there. How do we take other volume readings? Well, to be honest with you, we could use something like this. This is a graduated cylinder. It's got markings on it. And typically, when we put a liquid in a cylinder such as this, a glass cylinder like this, we typically will see this sort of curvature of the liquid. And let me just kind of exaggerate the drawing here, but get that out of the way here. So we typically will see this kind of curvature of the liquid, probably not that exaggerated. And this is what is known as the meniscus. And what's actually happening here is the liquid inside a glass container, like this graduated cylinder, there's a lot of attraction to the glass and the liquid. And what we get is the sides of the liquid will sort of rise up. And it will create this sort of meniscus that occurs here. And we always want to take our volume reading from the bottom of the meniscus. And that's because that truly is where the liquid actually is sitting in there. The sides are just sort of a result of the attraction between the liquid and the glass. So it kind of rises up on the sides, but the actual volume sort of level is really there at the bottom of the meniscus. So when you sort of take a reading in a glass cylinder, you always want to look for that meniscus. Sometimes it's easier to see. Sometimes it's harder to see. Something like a graduated cylinder is relatively easier to see than if you take something like a beaker, for example. Big beaker has a big opening. As you put some type of liquid in there, it's pretty spread out, the liquid there, and it makes it really hard to sort of visualize where the meniscus is. And that's why beakers are really terrible pieces of equipment to actually take a volume reading and measure out, while graduated cylinders, which has a much smaller opening here, allows you to better see that sort of meniscus and get a much better volume reading. That's why you never want to use something like a beaker to measure out a specific volume of, say, liquid. People are always surprised because even on beakers, they do have markings like 150 milliliters, for example. And people all the time will fill it up and go, cool, I'm at 150 milliliters. And then if they ever take that and kind of pour it out into a graduated cylinder, really measure how much volume they actually have, they usually will find themselves being nowhere near 150. And that's because that meniscus is pretty spread out and very hard to really dial in exactly where it's at. And that's why, again, there's certain pieces of glassware which are much better to take measurements with, while others obviously, are not the greatest pieces of equipment to sort of use. So in terms of volumes, liters, milliliters, we use a lot. Cubic centimeters happens a lot. And these are some important relationships. This one comes up a lot. In 1 liter, there's 1,000 milliliters. And again, you can basically use that as a conversion factor. This is a quart. I'm not sure where the T went, but 1 quart is 946 milliliters. That does pop up a lot, but I would say out of the two, definitely this one, we will see, you will use a lot. And again, it's basically 1,000 milliliters is 1 liter. And, if you had 1,000 milliliters, you basically want to turn it into a liter. You could just move the decimal point 3 places to the left, or vice versa. If you had 1 liter, you can move it 3 places to the right to get yourself to milliliters. So that's a very common sort of conversion that we use. Length is another common sort of measurement that we take. Very common units of length are meters. Also, other ones like centimeters, millimeters are very, very commonly used. A couple of relationships, there's 100 centimeters in 1 meter. So that's something that we use a lot. Also, kind of the relationship between the English units and the metric units in 1 inch, there is 2.54 centimeters. So if you ever look at sort of a ruler, you usually have sort of inches on top, centimeters on the bottom, and 1 inch would equal 2.54 sort of centimeters as well. There's 1,000 millimeters in 1 meter. So that's another relationship that we use. By the way, when we look at a regular ruler, usually, right, up on top, really bad drawn here, up on top are our sort of inches, right? On the bottom is our centimeters. And this is 1, so this would be like 2 centimeters, 2.54. And then all the smaller markings on the bottom of a ruler, these represent the millimeters, right? So inches usually on top of the ruler, centimeters kind of the bigger markings on the bottom. The little markings on the bottom are millimeters. There's 10 millimeters in a centimeter. So again, when you look at a ruler, that's sort of what you see here. So these would be centimeters. And again, these little markings here on the bottom, if you counted them, there would be 10 markings. Those would technically be the millimeters as well. Any questions on that there? And again, here are some of those conversions. That's very common. And, these are really what are referred to as an equality, right? This is what is referred to as an equality. An equality is basically two sets of numbers that are on different units, but they do represent the same amount of something. So for example, if you say you have 1 meter, that would be the same as saying I have 100 centimeters. Same idea. If you said, hey, I have 100 pennies, that's the same thing as saying you have $1. They're different units, obviously, but they do represent the same amount, in this case of money. You could pay in pennies if you went through a drive-through. You could pay in dollar bills. It's all money. But these are relationships, and very commonly, as we'll talk about later in this chapter, we can take these and use them as conversion factors. Like we could say there's 100 pennies in $1, or in $1 there's 100 pennies. And we could use this to, solve problems like if we had $5, how many pennies that would be, or vice versa, and so forth. So these type of things that we see here where something equals something else, again, different units referred to as an equality. And again, basically is what we typically will use for conversion factor type problems. Now, the mass of an object is really the measure of the quantity of material that it contains. There is a difference between sort of the couple of words that people sometimes use, which is mass and weight. And weight basically takes into account the force of gravity, but mass does not. So as we do a process when we weigh something here, sometimes confuses people, we do refer to this number that we get as the mass of the object. So in chemistry, you should refer to it as the mass of the object. Mass is independent of gravity. So the mass of the object here, the mass of the object on the moon would be the same. The weight of the object here and the weight of the object on the moon would be different because there's a different force of gravity. We use what is referred to as an electronic balance sometimes to weigh it, and that's what this is. A balance is a fancy word for a scale. You basically zero it out, put what you want on there, and then you read the readout there, obviously, as to what the mass is, and obviously is in certain units. Usually probably grams is typically the units that we see sort of on a balance. Here again are some common sort of mass relationships that we'll see. Again, this first one is one that we see a lot. 1 kilogram is 1,000 grams. And I would say this one we use a lot here. 1 pound is 454 grams, give or take 453.6 grams, basically. but a lot of people will round, so you can use the rounded number there. But these two relationships in terms of the mass is definitely ones that we come across a lot here in chemistry. And again, you should be sort of familiar with those guys there. Now, temperature is another sort of quantity of a measurement there that we make. And there's really three types of temperature scales that we talk about in this class, and that is degrees Fahrenheit, degrees Celsius, and as I mentioned earlier, Kelvin. Again, we do not use the degree symbol for Kelvin, as I mentioned earlier, but being able to sort of convert between these guys is really important. Really, the conversions come from the difference between where water freezes and where water boils on each of these scales. For example, on the Fahrenheit scale, water freezes at 32, boils at 212. On the Celsius scale, water freezes at 0 degrees Celsius and 100 degrees Celsius it boils. And on the Kelvin scale, water freezes there at, 273 and 373 Kelvin. So in chemistry here, we will use several of these, but really the conversion between temperature in Celsius to temperature in Kelvin is a conversion that we use a lot. And it's a fairly simple one. If you want the temperature in Kelvin, you pretty much take the temperature in Celsius and you add 273 to it. The actual correct number is 273.15. So sometimes you'll see this number. Most people kind of round off the 0.15 as it usually does get rounded off. So 273 is really good. Also means that if you have a temperature in Kelvin and want Celsius, temperature in Celsius would be the temperature in Kelvin minus 273. Again, out of the two here, this is one that we use a lot, converting it to Kelvin. Fahrenheit and Celsius also can convert. The temperature in Fahrenheit is equal to 1.8 the temperature in Celsius plus a 32. And the temperature in Celsius equals the temperature in Fahrenheit minus 32 divided by 1.8. 1.8 comes from like the fraction, maybe you learn 9/5. So if you do 9/5, that is 1.8. That's where that number comes from. So these are several different ways to convert temperature. You do need to be familiar with it. Again, I would say probably outside of this chapter, this is definitely the one you'll use the most. Outside of probably this chapter, probably won't see too much of these two, but you do need to know how to do it. By the way, if you're given something in Fahrenheit, for example, you then need to convert it to Celsius, and then from Celsius to Kelvin would be the order at which you need to do kind of do those conversions there. Any questions on that there?
Yeah, Professor, I have a question on the one to the right versus T Celsius with the T Fahrenheit minus 32 over 1.8. Which one is that one for?
That is if you have the temperature in Fahrenheit and you want to convert it to Celsius.
Okay, all right. So the one on the bottom is
if you have the temperature in Celsius and you want to convert it to Fahrenheit.
Got it. Okay, perfect. Okay, so I want to make sure. Okay, thank you.
Yeah, no problem. Any other questions? Okay, so again, you should be familiar with how to do these conversions, and we'll do some problems a little bit later, I think, as well. We'll actually put some numbers in. But again, after this chapter, probably this is your guy that you're going to see the most throughout the rest of sort of the chapters. And again, almost a safe bet on anything involving temperature and chemistry. You probably want to get that thing into Kelvin, and that's usually the units that you need. Time, again, the SI unit for time is seconds, and you should have some knowledge here coming into this class. Obviously, time may not be given to you as a conversion. So just to remind everybody, right, there are like 60 seconds and 1 minute. right? And 60 minutes and 1 hour. And again, only 24 hours in one day. Now, I say that because people go 60, 60 and go, cool, there's like 60 hours in a day. Thank goodness there's not. But that's a very common mistake that people make. Again, these may not be provided to you. You should hopefully, obviously, I would hope no time and stuff like that. But again, seconds is a very common unit in chemistry. If you just think about sort of logically speaking, if you were to run some experiments or something in chemistry, for example, very common experiments will run for seconds, maybe minutes or something like that. A lot of times we don't run experiments, for hours and days and stuff like that. It can happen, but usually very commonly things are sort of done in sort of seconds as well in terms of the time. All right, so let's take a look at each of these here. We want to know what type of unit is being described, length, mass, or volume. So if we look at 2.6 kilograms, kilograms is a unit of mass. So that looks like a 2 there. 1.7 meters. Meters is a unit of length. So that should be 1 there. Medication is 0.5 grams. Grams is a very common unit of mass, which would be 2. And lastly here, liters is a very common unit of volume, which would be 3 in this case. Any questions on any of those there? And again, it's really important to not only for you to include the units when you write a measurement or take a measurement, but it's also really important for you to understand when you see a unit, what is it referring to? So I'll be completely honest with you. I've had people over the years, lots of people sometimes go, hey, I got 5.5 kilograms. That's like my volume. And again, grams is obviously a unit of mass, and that should definitely tell you that it's not a volume, but it is some type of mass. So it is a very common thing that sometimes students, when they see a unit, it doesn't necessarily register to them that we're talking about like a length, or we're talking about a mass or a volume and stuff like that. So again, in addition, as I've mentioned, that's really important to be able to write the units with it. It's also very important to make sure that you understand when you see a unit, what is referring to. Again, later on, that could be very critical when you're trying to do some type of calculation. You go, oh, it gave me a volume, give me a mass. I could calculate something like density. But again, that recognition part is really important. So these SI units are sort of these standardized units based off of the metric system, as we talked about. Volume is really a meter cubed, although I'll be honest with you, in everyday chemistry life here, we really don't use meters cubed all that much. Again, liters or milliliters are very common units, but the SI unit would be that meters cubed. Kilogram, again, we do use a lot for mass. Length is meters, and temperature here again would be Kelvin as the common SI unit that would be used there. So if we look at each of these, we want to identify the measurement given is a SI unit. John's height is yard, feet, or meters. So again, as we just talked about, sort of the SI unit for height, which would be like a length measurement, should do something with meters here. Would make sense. The mass of a lemon, again, mass would be kilograms. Again, all 3 of these units definitely are masses, but again, sort of that SI unit is what we're looking for here. Again, would be kilograms. And temperature, again, the SI unit is our Kelvin. And again, like I said, all these are definitely temperature measurements. But again, the question here was asking specifically about sort of SI units. As we see there, that's good. All right, so now let's talk about really how to take a measurement, what are significant figures, where these guys sort of come from, what is the proper way of kind of doing these things and reporting these things. So when we take measurements, and we take sort of values when we do an experiment, for example, there's sort of two words that sometimes are used interchangeable, and they really do mean a couple of different things. So for example, if we talk about something being very accurate or accuracy, if something is an accurate measurement, it means that the number that you got is close to the true value. While if something is precise or has good precision, it means a group of numbers are close to one another. So what is the difference there? Well, if you think like maybe we're throwing some darts at a dartboard, right? The goal is to get really the bullseye there in the middle. So if I throw my darts to begin with, and again, goal kind of getting right there in the middle, and let's say I threw a dart, I missed the board, I got over here, and then I got one over here. Am I very accurate? And the answer would be, since the true value would probably be the bullseye in the middle, I'm not very accurate, right? I'm also not very precise. All three of these sort of darts are very far away from each other. They don't really line up well with each other. So this sort of guy would be both not accurate and not precise. If I take my darts and go, okay, we'll do like double or nothing, and I throw my darts and I hit them all basically right there. This again would be not very accurate, because we would want to kind of get to the middle there, which obviously we're far away from. But we are very precise, right? We basically hit the same spot every single time. This illustrates a good point that you can be very precise, but perhaps not very accurate, which means you could pretty much do the exact same thing wrong every single time, and it can be very repeatable, right? If you're not sure you're really doing something wrong and you just continue to do the same process over and over again, you probably will be very repeatable in terms of your values, but they may not be very accurate. Now, if I took my darts and then threw it again at the dartboard here, and I just littered the bullseye there with all three darts, I am very accurate because that's what I was aiming for. I'm also very precise. So typically speaking, if you're, fairly accurate, you probably will have pretty good precision, but you definitely could be very precise and not very accurate as well. Any questions about accuracy or precision? So when we take measurements, we kind of want to do both. We want to be very accurate and very precise if we're taking multiple measurements along the way. So let's talk about how to properly take a measurement. First, you need some type of tool to help you along the way with that. And we have a measured number. So a measured number is one, much like it sounds like, you use some type of tool to take a measurement. So how do we take a measurement? What's a good way to actually take an actual measurement, and the proper way to take a measurement? Well, the first thing that you always want to do is know that no matter what you do, there's always some degree of uncertainty when you take a measurement. So no matter who takes the measurement, there will be some degree of uncertainty. How much depends on really the equipment that you're using. So when you look at a piece of equipment like this ruler here, we want to look at what are the big markings represent and the smallest markings. So kind of the big markings and the smallest markings. Now, if you look at this, we have kind of an unusual situation, but not necessarily always unusual. Our biggest markings here are also our smallest markings. There's only one set of markings basically on this one. Each one represents 1 centimeter in this case. This is 1 centimeter, 2 centimeters, and 3 centimeters, and 4 centimeters, and so forth. Now, when you take a measurement, no matter what equipment that you use, there should always be some numbers that no matter who takes a look at it, everybody should agree. And those were referred to as certain numbers. So you always want to record all of the certain numbers. For example, if we look at this piece of wood or whatever it may be, no matter who takes a look at this, everybody should agree it is at least 4, right? Not really 5, but definitely at least 4. So you should always, when you take a measurement, record all of the certain numbers. So we would record 4. And this would be obviously all of our certain numbers. Now, when we look at this, clearly here, we are not exactly at 4. We're not really at 5. This is where really the uncertainty in this measurement comes into. I may look at it and go, I think that thing is like halfway there between the 4 and the 5. And I would record 0.5 centimeters. This would be my first uncertain number. Now, when you take a measurement, you always want to record all of the certain numbers plus the first uncertain number. And that 5 there is uncertain because somebody else may look at it and go, you know, I don't think it's really halfway. It's just a little before that. Maybe it's a 4, you know, maybe it's like 4.4. Maybe somebody says, I think it's a little further past half. Maybe it's 4.6 or something like that. That's really where the uncertainty lies. So always when you take a measurement, you should always record all the certain numbers plus that very first uncertain number. And when you do that, that really is what we call significant figures. Which means if I asked you in this particular measurement here, how many significant figures there are, you should answer 2 significant figures. The 4 and the 5 are significant. Where does the uncertainty lie in this particular measurement? The uncertainty lies right here in the 5. Again, basically by recording 4.5 centimeters, we're saying we think it's 4.5 centimeters, but maybe it's like 4.6, maybe it's like 4.4, which again, if you look at it, you know, it's in that range, right? Based on this equipment, that is the best that we can do. So always when you record a measurement, all the certain numbers plus the first uncertain number, that essentially is what makes up significant figures. Any questions on that? Now, you do want to kind of look at the piece of equipment because, again, different pieces of equipment have different sort of markings. So, for example, if I take something like a graduated cylinder and my really bad drawing here, which is probably why I failed art a lot. Yeah, that really doesn't look like graduated cylinder, but we'll pretend. We'll take this. This is 10. We'll go 20 up here, milliliters. All right, so we'll just say we have a liquid in there. We'll just do like here, there, meniscus somewhere. Actually, that's pretty thick. Let's not use that there. Let's go right there. How's that? We'll do right there. All right. Now, when we look at this, we want to always figure out what does each of the little scaling mean. So this is 10, this is 20. We want to count the little markings between the two. So also important, I'm not going to start counting on 10. I'm actually start counting on the next line. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 up there at 20. So if we count all the little markings there, there's basically 10 markings between 10 and 20 here. That means that each marking represents 1 milliliter. Like this guy here would be 11, next guy would be 12, this guy would be 13, This guy would be 14, 15, all the way up basically to 20. Now, if I look at my meniscus, we'll just say the bottom of my meniscus is like right there. We'll just go with that. Now, again, no matter who takes a peek at this, everybody should agree that it is at least 13 in this particular case. And again, we would record 13 as our certain numbers. But again, it's not exactly at 13, not really exactly at 14. It's somewhere in there. So we sort of imagine in between there. Again, I may say I think it is halfway there and record 13.5, again, milliliters. This would be my first uncertain number, which means if we count up all of our certain numbers and our first uncertain number, this would tell us that this number right here has 3 significant figures. It is telling us that maybe my volume there is 13.5, maybe it's 13.6, maybe it's like 13.4, which again, if you take a look at it, it does sort of make sense in that particular case. Any questions on that there? Now, when we sort of look at something like this, we can look back, for example, here. And if you look at sort of this marking here, the biggest and the smallest marking was basically 1 centimeter, which meant we were able to take it one more place to the right of the smallest marking. Here also was 1 milliliter, and we were able to take it one more place to the right. So if we had something like this, and we'll say this is again a ruler here. Now let's say we were measuring something like right here. So again, we would want to count up and see what we got going. So we got, this is 1. So counting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. This is 10 markings. Between basically 1 centimeter, right? That means that each of these little markings represents 0.1 centimeter, right? This would be 1.1, 1.2, 1.3, and so forth. So if we look at this, we could see that no matter who looks at it, they should agree it is at least 1.4. Again, our certain numbers here. Not exactly there. Let's just say for the sake of argument, we're a little past half. Maybe we look at it and go, I think it's like 1.47 centimeters. Certain numbers 1.4, uncertain numbers 7, meaning that all 3 of those would be significant figures. And this value here would have 3 significant figures. Uncertainty in that 7, again, could be as big as 1.48, 1.46, and that is, realistic based on what we are looking at there. Again, the smallest marking here is 0.1, first decimal place. We could take the reading one more place to the right. So typically speaking, we could go one more place to the right of the smallest marking. Not always the case. So for example, if you had if we count between these two guys, we got 1, 2, 3, 4, and 5 markings. So in this particular case, we actually have 5 markings between the 2 big numbers. That means in this particular case, each marking actually represents 2 milliliters. This would be like 12, 14, 16, and so forth. So for example, if our sort of water level or liquid level fell here, for example, that's between 14 and 16, which means the best we could do in that particular scale would be 15 milliliters, right? That's what happens between 14 and 16 is 15. There's not enough room in this spot here to figure out where like 14 stops and 15 starts, right? So the best we could do is 15, which means that this number would have how many significant figures? This number would have 2 significant figures. The uncertain number would actually be the 5. Maybe it's 16, maybe it's 14. And again, we're somewhere in this range, and that's what we see here. Any questions how to properly sort of take a measurement there? Always record all the certain numbers, always record the first uncertain number. 9 times out of 10, you could go to one more place to the right of the smallest number when you're taking a measurement. Let's also talk about, an important thing here. We'll steal this guy on the bottom here. Let's say we get rid of that there, and let's get rid of this. We got somewhere right. So let's say we were using this scale here, but we were measuring something like this, for example. Like you feel it's dead on that 1.4 sort of number. Now, what should you record? Should you record 1.4 centimeters? Should you record 1.40 centimeters based off of this scale that we talked about earlier? Now, you may say to yourself, is there really a big difference here between those two? And the answer is there really is a big difference here. If you take the 1.4 number there in terms of significant figures, this has 2 significant figures, which is basically telling people that the uncertain number is right there. And this could be maybe 1.5 centimeters, maybe it's 1.3 centimeters. That's a pretty big range. And if you look at the actual measurement, you can see that my line here is like nowhere near the 1.3 and really nowhere near the 1.5 number. That's a lot of error that you just introduced there. If I do this guy, which has 3 significant figures, the uncertain number would be the last significant figure, which would be this, which means it's maybe 1.41 or 1.39. Now, if we look at our scale, that is more realistic based on what we're able to measure out. So although you may think, well, it's not that big of a deal if I loft off the 0 here, it is a really big deal because there's a lot more error here between 1.5 and 1.3 than there is here between the 1.41 and the 1.39. You actually made your measurement a lot worse by doing that. So the correct way to do it is if you have the ability, for example, here to go to that second decimal place, and even if you feel like it's dead on that number, you should still record the 0, because if you get rid of the 0, you're really making it a worse measurement and also, creating a lot more error that shouldn't be there. Any questions on that there? So here, if we look at our wood piece, we did our 4.5 as we talked about earlier there. Again, the biggest number and the smallest number here represent the same thing. And again, represents 1 centimeter. We could go one more place to the right of that to take our reading. Again, it doesn't always have to be like 0.5. Again, if you felt like maybe it ended a little bit earlier, you could do any number you like there. Or if it was further this way, you could do something like 4.8 or something like that as well. Here is basically what we were just talking about here. If we look, there is basically 10 markings, starting counting here, between say 4 and 5. Each one again represents 0.1 centimeters. And if we look at it, this guy here would be 4.1, 4.2, 4.3, 4.4, 4.5, and then 4.6, not really 4.6 there. Again, everybody should agree at least is 4.5 And now we have our estimated digit there. Again, if you feel it's like halfway there, you could put a 5 there. This would be, again, all of our certain numbers, our first uncertain number. They would all be significant, and this would be 3 significant figures with this particular one here. Any questions on that one there?
Yeah, Professor. So when you give us problems like that, that's all you're gonna ask us if how many significant numbers there are, or are there gonna be more questions as we go on?
As we go on, we'll do some more stuff with the significant figure.
Oh, okay. But for right now, that's all we need to know, right? Just that we have 3 significant figures in the.
Yeah, we're gonna
Okay,
actually, what we're gonna talk about next is actually how you can look at a number and determine how many significant figures there are and stuff like that. But this is really for like when you take an actual measurement, you know, you want to make sure that you record to the proper number of significant figures because it does have a big effect on, you know, sort of the error that you're introducing or not introducing, depending on sort of, you know, if you take the proper reading or not the proper reading.
Okay, sounds good. Thank you.
Yep. Other questions? Okay, so we did that one there. We sort of covered this one here. Again, in this situation, they felt it was dead on the 3 because it is a whole number and the smallest marking is 1 centimeter. We do have the ability to go further off. And again, we do need to record it because what this would tell us is this particular number here would have 2 significant figures where the uncertainty is the 0, telling us it could be like 3.1 or 2.9, which is realistic when you look at where it's at. Again, if you just decide I'm just going to record 3 because, you know, it's on the 3, it makes sense. I'm just going to record 3. What you're basically saying is this is 1 significant figure, which means the error could be maybe it's 4, maybe it's 3, maybe it's 2. That's a very big degree of error we just put in there by eliminating the 0. And again, by just looking at it, you can see that that thing is nowhere near these guys, right? So we created a lot more error by lofting off the 3. We made the measurement a lot crappier in a sense by getting rid of that 0. So again, sometimes it's a very common error that people make. They get rid of that sort of 0. So you always want to look at your scale and see if you can go that extra spot. Again, you shouldn't put it there if you can't, but if you can, and you feel it's dead on a number, you should put the 0 there to maintain really sort of the accuracy of the measurement there. Any questions on that there? Okay, looking at this, I'm not sure if things shifted or not, but we'll hope it didn't. So this is 9 here. Looks like there are 10 markings between 9 and 10. Each one should then represent 0.1 centimeters. So this would be 9.1, 9.2. Again, it looks like almost is dead on 9.2. So again, we would not want to record this because we do have the ability in this case to go one more place to the right, which means we actually should record this guy here as the correct one. This would have 3 significant figures in this particular case, where the uncertain number would lie right here. Again, if we sort of loft off that 0, we're now moving the uncertain number to here, making it a much worse measurement than it should be. Any questions on that one there? All right, so that's really important when you take those measurements that you always look at the scale, figure out how far you can take it, and make sure that you record all those things. Let us talk about sort of the rules for significant figures and how to count significant figures. So in a measured number, the significant figures are all the digits that include basically the certain numbers and that estimated digit or that uncertain digit. First rule is pretty simple. All numbers that are non-zeros are significant. So if you had 2, 3, 4, 5, we always start counting left to right. We want to always count our significant figures. Once we hit the very first non-zero, this would be significant, 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 which means that this number here would have 4 significant figures. Now, the zeros are the next thing that we talk about, and the zeros get people in trouble sometimes. There's 3 types of zeros. The first type of zero is sometimes referred to as a leading zero. And a leading zero are not significant. So for example, 0.000227. We start left to right, all of these zeros are not significant because we really haven't started counting yet until we hit this number here, which is our first non-zero. That is a 2, which means that's significant. The next 2 is significant. The next one, 7, is significant. This would have 3 significant figures, this particular number. Kind of like placeholders are sometimes referred to. Any questions on that one there? Then we have what are sometimes referred to as captive zeros, trap zeros. And these are basically zeros between 2 non-zero numbers, and these guys are significant. So if you had 4004, we would start counting here, which is our non-zero. These 2 zeros are trapped, which means they're significant. This is a non-zero at the end. This number would have 4 significant figures. Any questions on that particular one there?
Sorry, because I didn't hear the last one. Okay, so the ones with the zeros between so there's 4 total significant figures.
For this very last one we were just talking about?
Yeah, so we do count the zeros.
You do. So
Okay.
there's basically 3 types of zeros. The first type is like up here, where we get all these zeros before we hit the first non-zero number. So those are not significant. When you have zeros that are between 2 non-zero numbers, they are significant. So because we start counting out the first 4 here, then these zeros are really trapped between the 2 4s in this particular example. They are significant in that case.
Got it. Okay, thank you.
Other question? Now the last zero, which is really the one that gives people the kind of difficult time, is what is referred to as a trailing zero. And that's basically a zero that comes at the end. And it may or may not be significant. What makes it significant, those zeros, is if there is a decimal point in the number. Now, the decimal point does not need to be right next to the zeros. You just need a decimal point in that number somewhere to make those zeros significant. So for example, if I did 400 written like this would have only 1 significant figure if this was a measurement. First significant figure would be here. These are zeros at the end. There's no decimal point in that number, so they are not significant. If I take 400 and write it like this and put a decimal at the end, this decimal now turns these guys significant. We would start counting here at the 4. These 2 zeros would be significant, and this would have 3 significant figures, this particular number there. Question on that one there.
Professor.
Yeah.
So I still don't understand why the first one that you just placed right now was only 1 significant figure.
So when it is written like this, if it was like a measurement and nobody wrote a decimal point in this particular number, what that is,
because it's an exact number.
Yeah, it's not an exact number. It actually would have 1 significant figure, and it would be just the 4 here. And basically what that would be telling you is this could be as big as like 500 or as low as 300 for that error. That's a lot of error, right? Because there's only 1 significant figure. It's kind of a bad measurement, right? There's a pretty big range of, where this guy should really be. If we ended up having a way to take a measurement where we would put the decimal point there, that then turns these zeros into being significant, and it also makes it a much better measurement because now the uncertain number is this last 0, which means that number there means that it could be like 401 or like 399, right? A lot less room for error. So the significant figure rule is if you have zeros to come at the end of a measurement or a number, those zeros will be significant if the decimal point is actually written into the number. If there is no decimal point written, then it is not considered significant, those zeros at the end. Question on that?
Is needed in this. No, thank you so much.
Professor,
Yeah.
if the number was 400.0, would that make it 4 significant figures?
It would, yeah. So
Okay.
again, here we would start counting at the 4. All these zeros would be significant, and it would have 4 significant figures in that particular case. Exactly. Now, let's say, for example, you took a measurement like 0.0004004003200. I'm not sure how you would get that measurement, but let's just say this was a measurement and we want to figure out how many significant figures this guy would have. Now, when we look at these zeros here, these would not be significant because they're leading zeros. We really wouldn't start counting until we hit this 4 that's right here. Then we come across 2 zeros that are trapped between non-zero numbers, which means they would be significant. Obviously, the 4 is still significant. We then come across another set of zeros that are trapped between 2 non-zeros. So those would be significant. This guy would be significant. Now we come to the zeros at the end. Are these zeros at the end significant? The answer is yes, they are, because way over here, there's a decimal point, and that would make those zeros at the end. So the decimal point doesn't have to be right next to those zeros. It just needs to be somewhere in the number for it to be significant, which means I lost count, but it looks like this number would have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 significant figures. Any questions on how to count significant figures?
Yes,
Yeah.
Professor.
Oh,
Sorry.
No, you're okay. Go ahead.
One more question. If it was like 4.00, that would be 3 sig figs also because of the decimal point.
It would, yes.
Okay.
Now, sometimes people will look at like these zeros here that we looked at, before and go, well, doesn't these zeros come after the decimal point? And they do, but we have not started counting really significant figures until we hit the first non-zero. So again, even though they come after the decimal point, we're not counting those because they're still leading zeros because we haven't really started counting our sort of significant figures at that point. Was there another question?
Yeah. So Professor, the one where it says 1 significant figure. So let's say it was like 5,600 with no decimal.
Sorry, did you say
So yeah. So let's say you wrote 5,600 like that. Just say with no decimal. Would there be only 2 significant figures?
There would be, and it would start counting here, and this would be significant. These guys would not. So the uncertainty here would lie in this number.
Okay, got it.
So that's also a very good sort of question. Is sometimes you're asked, where is the uncertainty in a particular measurement? And the uncertainty in a particular measurement is not always the last number that you write, even though sometimes it is, and a lot of times it is the very last number you write. But the uncertainty always lies in the last significant figure that you write. So in this case, the 6 is our last significant figure, and that's really where the uncertainty lies, which means, again, this could be, as high as 5,700, as low as, say, 5,500. Again, a pretty big room for error there, and not the greatest measurement. Same thing here. This guy, as we said, 500 or 300, not a good measurement compared to this guy where the uncertainty is back over here with this digit. So when you're asked where does the uncertainty, the estimated digit, or something of that nature, what we're talking about is the last significant figure is where that uncertainty or estimation is basically played or put. Other questions on that? Now, here's some numbers, and again, it kind of got a little messed up, but we got 2 significant figures here. This is 5 significant figures here. I'm not really sure what we got going here. We got 4 significant figures here. Again, 15, no decimal point written, 1 significant figure. We talked about scientific notation earlier. when you write a number like this, or, when you write a number in scientific notation, all of the numbers that come before the times 10 part, so all these numbers that come before the times 10 part are always significant. So these are always significant, which means that this number written in scientific notation has 3 significant figures. This number here in scientific notation has 2 significant figures. And again, always in scientific notation, all the numbers before the times 10 part. The nice thing about that is sometimes the only way to get something into the correct number of significant figures when you do a calculation is by writing it in scientific notation. And you can kind of control how many significant figures you have by going, well, if I need like 2 significant figures, I could write something like this. If I needed 3, I could write something like this, and so forth. So you could kind of write it in scientific notation. You could kind of control how many significant figures you would have with scientific notation, but always all the numbers that come before the times 10 part should always be significant when you write it in scientific notation. So if we look at these here, this has got, again, 4 significant figures, starting to count with the 3. They're all significant. This has 2, starting with the 5, 6, obviously, the 3, and starting with the 1 here, all these guys would be significant, which would give us 5 significant figures. Again, our zeros, these are trapped zeros, so these are significant, so that's 4. This is a trapped 0, so it's significant, so that's 3. These are leading zeros that don't count, but then we have our trapped 0 after we start counting here, gives us 3 significant figures, and obviously here, leading 0, start counting here, significant, significant, trap 0, significant, and significant. So 1, 2, 3, 4, 5 significant figures here. Again, always want to start left to right there and make sure that you count up all your significant figures as you go to the right. Any questions on that there?
Yeah, Professor Ephron.
Yeah.
Quick question. The first one, the 50.08. I need some clarity. So let's say it doesn't have the decimal. I'll still consider it 4 significant figures.
Yeah, so in this particular case, the decimal really doesn't matter because the only zeros that you have are these 2 zeros here that are trapped between 2 non-zero numbers. Yeah. So they're considered those kind of trapped zeros or captive zeros, which means they're always going to be significant. So regardless if the decimal point was there or not, those zeros would be significant. For example, if you just wrote 5008 like that, it would still be significant because they're trapped between 2 non-zero numbers. So the decimal is only for any zeros that would come at the very end of the number. Is for that. That's really where you want to concern yourself with the decimal.
Okay.
Other questions on that?
Yeah, Professor,
Yeah.
on the same number, 50.08, if it read 50.080, would that be 5 or 4 still?
I'm sorry, so you said 50.080?
080?
Yeah.
Yes.
Okay, so what do you think it would be? How many?
Would it be, because on the last chart you said it'd be 5 because it was the point decimal, right? So would it still be 5 or 4?
It would be 5 in this case. So again, if we were to count this, we would start here with the 5, which is our first non-zero going left to right.
Mhm.
These 2 zeros are technically trapped zeros because they're between these 2. So they are significant. The 8 obviously is significant because it's a non-zero. And now really at this point, we have this 0 at the end, and that is where we want to look at this number. And again, the decimal point doesn't need to be near it. We just need to make sure there is one, and there is one right there, which would make it significant. So this guy would have 5 significant figures.
So it doesn't matter whether it be 1 0 or 3 zeros, they'd all be significant?
If you mean like at the end, if you just kept
Yes.
piling on zeros there. So if you
Yes.
just went like something like this, yeah, every single 0 I would write at this point would all
Mhm.
continue to be significant. Because
Okay, all right, perfect. Thank you.
Yep. Other questions on that?
Yeah, Professor, when you say trap zeros, does that only occur when it's 2 zeros together, or could it be like 5 0.008, you know, like could it be 3 zeros that consider?
Yeah, so it could
Okay.
be as minimum as 1 and as many as you like.
Okay, all right, that's what
As
I
long
wanted
as
to say.
sort of at the beginning, there's a number, and then however many zeros you got going on there, if there happens
it.
a non-zero there, they would all be significant. Or if you just simply had 1 in the middle there, it would also be significant as well.
We could also call them trap zeros because I keep noticing that when it's only 2 zeros in the middle that you say trap zeros, but
Yeah, no.
is-
So for example, this guy right here would be a trap 0. That 0.
oh, okay, got it. That's all. Okay, this is what I wanted to know. Okay, I
And
got it.
this guy, these zeros right here are also trap.
Are trap zeros as well.
Yeah.
Okay.
So trap zeros, or again, sometimes people call it captive zeros. It's basically just any amount of zeros that are trapped between basically 2 non-zero numbers makes them significant, basically. And it's really because you have a non-zero number that comes after it, which means that's going to be a significant figure, which by turn would turn those guys into significant figures as well.
Okay, got it.
Other questions?
Thank you.
Yeah. Professor Efron, quick question. On that example, 500, 0, 8, and then all these other zeros in the end,
Yeah.
all those zeros in the end was still kind of significant figure?
They would, because I circled it, so it kind of looks like a 0, but that was a decimal there originally. So because there's a decimal there, all these zeros would be significant. Yes.
Because the eight's in front, right?
It's really because there's a decimal point here when we're talking about the zeros at the end. So all zeros at the end become significant if there's a decimal point anywhere in the number. Again, it doesn't have to be right next to them. You can have that decimal point way up front and a bunch of zeros. And then you start writing all these zeros at the end. Again, we could start counting here, and none of these would be significant because we have not hit a non-zero number yet. As soon as we hit the 1, that is now our first non-zero number. And that's really where we should start counting our significant figures. And now what that means is all these zeros are basically at the end, right? And these would become significant because way back over here, there happens to be a decimal point in a number.
Okay, got it.
So in
Thank
that case, it would be something like 6 significant figures. Other questions on that? Okay.
Thank you.
Yep, you're welcome. So we will lay it up there for now. So happy